All right, I want to talk about random walk theory, simple random walks. And I want to talk about exactly how the results in random walk theory actually give you results in gambling, right? Simple results in gambling, right? So first of all, what is a simple random walk? What's a random walk? What's a simple random walk, right? So first of all, we're going to work on a lattice structure. A lattice structure is like this, right? Essentially, in two-dimensional space, a lattice is the set of all integer coordinates for both the first and the second coordinate, right? So it's two-dimensional space. So, only integer valued for both the x and the y. And so we're going to transverse this lattice structure. So we're going to start at a given point. Let's just say I'll have, start here, and then you can move here, move here, move here. Oh, you can go back, and then you just, leave, and then you come back, and you just walk along. So it's a walk. It's just, just a walk. So I guess it's like a street grid, right? And you're walking along the street grid. What's interesting, so that talks about a walk, right? So what's a random walk and a simple random walk, right? It's simple. Well, if you're at this point, let's just say, you can only walk to the neighboring lattice points. So you can only move to lattice points that are touching that lattice point, right? So from here, you can move up, down, left, or right, and that's it. So in two-dimensional space, obviously three-dimensional, you have more, you have four, whatever. We're just talking about two-dimensional space here. And so two-dimensional space, you can move left, right, up, down. And why do I want to focus on two-dimensional space? Because it's easy to visualize. You know what I mean? I don't need anything that's hard to visualize. We don't want to get into 10-dimensional space where, you can't draw it. And three-dimensional is going to be kind of nasty. This is okay, right? So this is reasonable to look at. And so usually when you talk about random walks, everybody looks at the picture in two dimensions, but the results you talk about are more in two dimensions. So you just visualize it in two, and then you go do your thing in more than two. It's no big deal. So, but I'm not going to draw three. I'm not going to be able to draw three. So, okay. So a random walk has essentially the same probability of moving from a given square, let's say a given lattice point, this lattice point, to these four, up, down, left, and right. So it has a probability, since there are four different ones, so it would have a probability of 1/4. So it'll be a simple random walk. And that's it, right? So, you can go up here with probably 1/4, and then over here probably 1/4, because once you're here, it's still up, down, left, right, 1/4, etc. And this is obviously an infinite lattice. So this process just continues. And so the picture I have here is two-dimensional, which is fine. And I'm going to state two results. And these results are very interesting. And I'm going to, and they actually apply. One of the results applies to gambling theory, right? Well, just gambling itself, not gambling theory. Gambling theory is different. Okay, so first of all, the statement is that in one two-dimensional space, these simple random walks are recurrent. What does that mean? That means that every single point you see here and the points you don't see here, this random walk, as it continues forever, will visit each and every one of these points infinitely many times, infinitely often with probability 1. So it's just going to come back, leave, come back, leave, come back, leave, come back. It's always going to come back. It's always going to come back to every single point. And that's in dimension 1 and 2. And dimension 3, which I'm not going to draw because it's going to be too much, it turns out it's transient, which means there's a positive probability it'll never come back once it leaves. Right? It may come back. I mean, really, if you're in three-dimensional space and you move up, you might come back down, and you're back to where you started, It's possible, you know what I mean? You're going to need something else. When you're in three-dimensional place, you're not going to want up, down, left, right, because, you have a third dimension. So you might want to use just x left, x right, y left, y right, and z left, or, z left and right, and left meaning down, minus, and right meaning plus. I mean, usually when we talk about left, it's on the number line, so it's minus. So you go down in that coordinate. So you have all these coordinates, x, y, z, and then either down or up. So I was using left and right because that's what I was using before. No big deal. And that's one way to designate the motion in three-dimensional space. But the fact is, there's a positive probability you'll never come back to a place you visited. And so there's a joke that mathematicians talk about, about random walks. And the joke goes that if you have, a drunk guy at a bar, and he doesn't know his way home, and he just randomly goes around town, making left, making right, going this way, going that way, whatever. Eventually he'll find his way home. Because a random walk is always going to take you everywhere. It'll take you everywhere on earth, you know what I mean? Literally. Eventually. It might take a long time for him to make his way home, but eventually he'll get it there, which is good. However, if you have a drunk bird, a bird travels in three-dimensional space. And yeah, assuming that the bird travels like in the lattice, which obviously isn't true, but for this example's sake, let's just assume it is. Like the drunk guy makes sense in a lattice because he's going from street to street, in the cross section of the street. But a bird flying, that's a little not so much lattice style, right? But for the joke, it's okay. And the statement is a drunk bird would never find its way back home because in three-dimensional space, it's a positive probability. It's just not going to come back ever. So it's kind of interesting. Okay, so we have that result, and that result is what we need because when we're in one-dimensional space, we essentially are moving left and right. We start at zero and we move left, so now we're going to talk about gambling. And so if we're talking about gambling, the negatives is kind of like losing, okay? You lose $1, you lose a match. It could be $10, $100, $1,000, $1 million, whatever. But you just lose one, you lose two, you lose three, you lose four. And to the right, you win one, you win two, you win three, you win four. And sometimes you go right, you go back left, and you can get back to zero, which, in the gambling context means, I guess you break even, right? Assuming you don't have to pay to play, which I think is normal. All right, so that being said, this is a random walk. This gambling dynamic is essentially a random walk in one-dimensional space. And so it's recurrent, which means we're going to move all as far to the right as we can imagine and then some. And the same is true to the left. And I'm assuming the probability is a half of winning and lose. So it's a simple random walk. And mind you, if the probability is not 1/2, everything I'm going to say is still true. Right? If the probability is P and P is not equal to 1/2, everything is true. There's just some drift, but you still move all the way to the right as far as you can imagine, then some, and move farther to the left as much as you can imagine, then some. There's going to be drift, so it's going to lean to one side, but it'll always come back. It'll come back. So, all right, good. Anyway, so in this game, we're going to win so much money we can't imagine. We're going to lose more money we can imagine. The problem is that the casinos have unlimited money because they print their own chips. They make these chips. They do. They make chips. They make the chips, which is a big deal. However, gamblers, they don't have unlimited money. And the minute you lose all your money, you're done. You can't continue playing. You can go, you can go down a bit, whatever this is. Let's say this is $10,000. You lose 10, 20, 30, 40, 50, around $100,000 we're done. No more, no mas, we're done. Whereas the casino can lose 100,000. You can be, you'd be on the right. They would lose 100,000. It's nothing. They can lose millions. It's really, I think in the millions it means something, but overall, over a year's period of time, I actually would bet that it's not that big of a deal. So the fact is, if you're going to move to the right really far and you're going to move to the left really far, however, you're cut off on the left when you lose too much and you're not cut off on the right. And you're not, okay. It seems as though you're probably going to end up losing if you're cut off. The minute you're cut off, you're done playing. Whereas the casinos, you can go right. Casinos can keep playing. knowing full well eventually you're going to go to the left, and eventually you're going to lose out by everything you have. So, the concept that these random walks, these simple random walks are recurrent is bad news for gamblers. So you're going to have to, if you're going to gamble, you're going to need to use something more than just random luck, because the casinos have so much more money than you do, that they can just kick the can and wait. And eventually, if everything is equal, they will win. Thank you for watching.